Most prior works in continual learning restrict memory due to cost or privacy reasons. We first analyze cost and find out that the cost of storage is far lesser than the cost of compute, meaning limiting memory does not help cost. Similarly, simply limiting access to past data doesn't help with privacy as models remember data and and we can retrieve this data back. Privacy needs forgetting, which is incompatible with continual learning. Hence, we address a new setup where our goal is to reduce computational costs with no restrictions on storage. We analyze past three directions taken in continual learning: distillation, sampling, and FC layer corrections, and benchmark them on our new setup. We find that all three directions fail when computational costs are equalized. The best thing to do is to simply take a balanced subset of data and train using all the computational budget. Now we discuss our work in greater detail. First, what is continual learning? Here, we want to continuously update our learner based on new incoming data from a stream S revealed over time. This involves three steps typically. First, the stream reveals a set of image label pairs from varying distributions. Then we get the new data and concatenate it with the previous data and create a bigger memory. Then we train our continual learner on the new data and the memory. Typically, past work limits access to memory. This is because of cost or privacy reasons. Let's analyze them. First, cost. We see that the cost of storing past data is far lesser than the cost of compute, hence is not a good reason for limiting access to past data. Similarly, for achieving privacy, we cannot simply restrict access to past data, as deep networks memorize information, and privacy, we need to achieve complete forgetting, which is incompatible with continual learning. So what do we do? Instead of limiting access to past data, in our setup, we say we should restrict compute. So we can store all past samples. However, when we want to update our continual learner, we only have a computational budget CT to spend. Notice that limiting computation implicitly restricts memory. How so? Let's check with a concrete example. We take the dataset ImageNet2K, which consists of ImageNet1K plus 1000 more classes from ImageNet21K. The setup is such that we start with a pre-trained model trained on ImageNet1K, and we want to learn the new 1K classes without forgetting the old 1K classes. When we say our budget, our experiments typically involve computational budgets ranging from 0.5 epochs to 0.25 epochs of the data, which is very small. Similarly, we test on a CGLM dataset, which is transfer learning from the ImageNet1K pre-trained model. We consider three types of streaming settings. The first two are for the ImageNet2K dataset, and the third is for CGLM. In a class incremental setting, the incoming data consists of new classes. In a data incremental setting, we just shuffle data and present chunks of data across time. In time incremental setting, we order the data by the upload time to the server. So a chunk incoming represents the natural flow of time, hence being more realistic. What we do in our paper is we analyze existing CL methods. We first divide them into three principal directions: distillation, sampling old data, and correcting the FC layer. We now see how do these perform in our computationally budgeted setup. We present our experiments here in CGLM, but present more extensive analysis in our work. We first compare sampling strategies. We compare each sampling strategy to the best case scenario, which is training a model offline using all past compute using the current accessible data. We see that most cheap sampling strategies perform roughly equally, with class balancing often performing the best. However, expensive sampling strategies waste the computational budget, lowering the performance, as some of the budget is required to pick the samples itself. Hence, do not spend any computational budget on expensive sampling. Just train your model with the budget. Now onwards, we shall be using this baseline, the class balance baseline, to compare all further methods. Then we check distillation. Does distillation help? We see that distillation has overhead computational costs compared to the naive baseline and hence does not help. It is simply better to train a model without distillation. Does FC layer corrections help? While they take little to no compute, we see that they perform equal to or worse than the naive baseline without any FC corrections. Hence, we still think we should still train a model with all the budget, with no corrections whatsoever. Now we see how does this perform under different computational budgets. We analyzed under 2000 iterations in the past experiments. What if we make it 800 or 8000? If we reduce the computational budget, we see that the methods diverge, that is, go further out from naive. Hence, restricting computational budget favors the naive method. The more restricted you are, the more inclined you should be to spend all your budget simply learning. And when we extend the budget, we see that more or less all methods perform equally. That is, the overhead cost of distillation methods such as cosine or MSE isn't as large. However, this does not mean that when we increase the number of iterations, they outperform naive. They just converge to the same point as naive. In conclusion, existing CL algorithms do not help in a computational budgeted setup. The naive baseline of just class balancing and training using all your compute budget outperforms all considered CL methods. The above conclusions are persistent across varying computational budgets and varying amount of time steps. Thank you.